In this lecture, we will discuss about concepts of hyperconjugation. So what is hyperconjugation? It is electron delocalization from a bonding orbital to a unfilled orbital. Let us discuss this with the help of a carbocation. So we have a carbocation. This carbon is sp2 hybridized and this carbon is sp3 hybridized. So about this carbon molecule is tetrahedral, about this carbon molecule is planar. So we will have something like this. So this carbon has two hydrogen, one is going inside, another is coming outside the plane of paper. Now this is sp2 hybridized, so 2p orbital is used. So we have only used 2p orbital, 1p orbital is left. So this carbon will have 1p orbital, that is empty, and this will have positive charge. So this p orbital is empty. So this is a empty orbital. Now this is sp2s overlap. So this is sp3s overlap. So this carbon hydrogen bond is sp3s overlap. Now this p orbital and sp3s overlap orbital lies in same plane. So we can say in this case sp3s overlap orbital and p orbital lies in same plane. So what is possible in this case? Electron can flow from this carbon hydrogen to this orbital. So basically there is a flow of electron from this bonding orbital to this unfilled atomic orbital. We can show this same using the orbital picture diagram. So we have a carbon hydrogen and this has a sp3 orbital that is overlapped with hydrogen. So let us show this carbon hydrogen bond by orbital. So this orbital is sp3 and this orbital is hydrogen s. Now we have carbon, one hydrogen is going in, one hydrogen is coming out. So what will happen in this case? Electron cloud can flow from this sp2 orbital to this p orbital. So basically there will be a bonding possible between this orbital and this orbital. So what will happen? Due to this flow of electron, this bond can break and there will be a double bond between this carbon and this carbon. And this hydrogen will have a positive charge because this bond has broken. So this is called a hyperconjugating structure. So this one is hyperconjugating structure. The same thing we can show by this kind of three-dimensional orbital picture diagram. So this is p orbital, this carbon is sp3 or hybridized orbital, this is hydrogen. So electron can flow from this sp3 hybrid orbital to this p orbital. So basically there is an overlap between sp3 and p orbital. This kind of overlapping is called hyperconjugation. Hyperconjugation is also called no bond resonance because these two structures are very similar to resonance. If you see, we can write the same thing. So we have carbon hydrogen plus charge. So we have to break this bond, and then we can write hyperconjugating a structure. So CH H, I will have a double bond here, CH H. This is a hyperconjugating a structure. Hyperconjugating a structures are shown by double-sided arrow. In this case, we can draw three hyperconjugating a structure. So let us try to draw all the hyperconjugating a structure for this carbocation. So we have CH H. One time we can break this carbon hydrogen bond, another time we can break this carbon hydrogen bond, another time we can break this carbon hydrogen bond. So we can write three hyperconjugating possible structures. So let us break this bond. So I will have hydrogen will be positive. So this is one hyperconjugating a structure. If I break this bond, I will have another hyperconjugating a structure. And hydrogen will have a positive charge. So this time we can break this carbon hydrogen bond. Then we will have this hyperconjugating a structure. So there are three hyperconjugating a structures are possible. So in this case, three hyperconjugating structures are possible. The hydrogen that participates in hyperconjugation is called hyperconjugable hydrogen. So the hydrogen that participates in hyperconjugation is called hyperconjugable hydrogen. For example, in this case, we have three hyperconjugable hydrogens. So you see, this hydrogen, and this hydrogen participates in hyperconjugation. So for this molecule, we have three hyperconjugable hydrogen. For example, if I ask how many hyperconjugable hydrogen we have for this carbocation, so we have this hydrogen is hyperconjugable, this hydrogen is hyperconjugable, this one is hyperconjugable, this one is hyperconjugable. So in this case we have 4 hyperconjugable hydrogen. If you see what hyperconjugation does, basically hyperconjugation makes electron cloud more delocalized. If you see, we have 3 possible structure hyperconjugating a structure. This is 1, this is 2nd, and this one is 3rd. So in these cases, we can flow this electron from this bond pair to this bond pair. So hyperconjugation is basically delocalization of electron. Is delocalization of electron. Any process that delocalizes electron or disperses electron makes molecule more stable, like resonance, hyperconjugation, or we can have inductive effect. These can basically disperses electron and makes molecule more stable. Hyperconjugation can be used to decide stability of carbocation. For example, let us say if I have this carbocation, this is a tertiary carbocation. Next we can have this carbocation. This is a secondary carbocation. Or we can have this carbocation, it's a primary carbocation, or we can have methyl carbocation. Now if you see in this case we have 3 plus 3 plus 3, 9 hyperconjugable hydrogen. That is, we can write 9 hyperconjugating structure is possible. In this case we can have 3 plus 3, 6 hyperconjugable hydrogen. So 6 hyperconjugating structures are possible. In this case 3. In this case also we will have 3 hyperconjugating structure. In this case we have no hyperconjugable hydrogen. So none of the hyperconjugating structure we will have in this case. We know more the hyperconjugating structures, more the delocalization of electron, more the molecule stable. So this carbocation is most stable. Then we have this carbocation. Then we have this carbocation. So stability order we will have. So we will have this carbocation most stable. Then we will have CH3 2 CH plus. Then we will have this carbocation, and finally we will have methyl carbocation. So stability order increases in this direction. So in short we can say this is a 3 degree carbocation is more stable than 2 degree carbocation is more stable than 1 degree, and this is more stable than methyl carbocation. The same thing we can show by potential energy diagram and flow of electron density. So this is a electron density map. If you see for a 3 degree carbocation, that is this one, CH3 CH3 CH3, that is tert butyl carbocation, electron cloud is delocalized. So you see here we have electron cloud, here we have electron cloud, here we have electron cloud. But if you see isopropyl, that is 2 degree, electron cloud is slightly localized. In case of ethyl, electron cloud is more localized. In case of methyl carbocation, electron cloud is highly localized. So in case of methyl, electron cloud is low localized. But in case of tert butyl, electron cloud is delocalized. So this is most stable. and this one is localized, so this is least stable. Let us do a small problem. So we have given 3 carbocation, we have to find a stability order. This carbocation is primary, this carbocation is tertiary, and this carbocation is secondary. So tertiary is most stable, so B is most stable, then we have C, and then we have A. So this is the stability order.